Will be familiar to you from that course, but for others in the Petroleum Institute it may not be.
I'm glad I took that course.
So but we are going to go into the numerical way of how to find these things, which we didn't do in another course. Okay, this is I guess on record, just to access, how to access COMSOL for LSU people. I hope at the PI you will have your own license. So at the LSU you can borrow the disk from us, and while you are installing the license, the installation software will ask you for these two pieces of information. One is the server, ChE print LSU. The other one is the port number. If you enter these two, then it will automatically link up your installation with the license, the classroom license kit from there. Okay, so there are two more people from the PI. Bisu Netanosius. Good.
There's a giant puddle.
Giant?
Oh, yeah.
You have COMSOL, right? We have access to it.
And I have mentioned.
Do you need access to COMSOL? You need the disk? Okay.
Like a PVC pipe coming out of the ground at the end of the room.
Really?
And probably is the source of water.
So I would request both of you, once you install it, either bring it back to me or circulate it among your friends, but keep track of who you gave next. Okay, in the so that. So just one more time, I will point this out. There are two CDs that are in circulation for installing COMSOL on your own machine, and when you are installing it, it will ask you for two pieces of information. One is the server, which is this address, and the other one is the port number, and you must enter this, and then it will check against the license, and you'll be able to use COMSOL on your local machine, as long as you are on campus. If you are off campus, in addition to that, you need something called a virtual private network, and that will be, I think it's called Cisco. Cisco AnyConnect. Okay, so you should be able to download that software from Tiger Bytes and install it on your PC. Then from outside, when you start that program, it will ask you for LSU authentication. And once you authenticate yourself with your LSU user ID and password, then it is as if you are on the LSU network, even though you may be far away. And so you'll be able to access the license server and able to use it. Okay, so those are the two instructions about COMSOL. And your next assignment should be coming to you using COMSOL sometime this week. I haven't started working on it, so maybe by Wednesday. But your project list should be up by end of today or early tomorrow. And I would request you, it's going to be first come, first served, so pick a project and let me know. And I will keep the Moodle page updated with available projects at the end of every day. And you should start working on it, so you'll have 2 full months to work on it. And the presentations, project reports will be scheduled in the first week of May, including your final oral exam. So all these 3 things will be based on the project. A report will be needed, and a presentation in class will be needed, and a half an hour oral exam, which will be based on the project, but going in deeper into algorithms that you have used in solving the problem in COMSOL. You won't have to do any programming other than writing, making it solve in COMSOL and generating the results and analyzing the results. Okay, any questions? I hope you found Mrinal's introduction to COMSOL useful, and he is an expert. He's in fact going to work for COMSOL, so you're getting the best thing from him. And I will ask him to record a few more sessions on solving ordinary differential equations, partial differential equations, coupled partial differential equations, etc. Over the next several weeks once he's back. Yeah, please. Disu, go on. I have a small question. What is it? I'm sorry, we haven't been able to figure out audio, two-way audio communication yet, but we will use the chat. Are we getting the video lectures from ComSol? Yes, you are. Mrinal Jain has promised that. So he's going to record what he did in the. He didn't record it. Mrinal is already there. Sorry about that. I will upload it this week. Okay. So you got the answer straight from the horse's mouth. Yeah, I think it is important because when you show something, all you learn is what I call the art of the possible, what is possible. But how do you do it yourself? When you go sit in front of ComSol, you will be stuck. So it is nice to have a video on the side and see at least at a slower pace how he accesses various menus and stuff like that. There are two things that you need to learn any new software and use it intelligently. One is what is in the software in terms of the algorithms, the solvers, the models, and stuff like that. That's what we're doing in the class. The other one is a particular syntax of a programming language or a particular sequence of menus that you have to access to set up the problem. There are lots of built-in models in ComSol one can use to kind of learn on your own, but we are trying to give you a little bit of help with additional recording from Mrinal. And so both will hopefully accelerate your learning of ComSol. With voice, meaning you cannot hear my voice? Are there people online who are not able to hear my voice? Please let me know. Oh, you're talking about recording. All right, sorry. But you guys are able to hear me clearly, right? Okay. All right. Not sure how many people have dropped out because we have a smaller number here. 2, 4, 6, 7. All right. So I guess about a week ago when I gave the last lecture, we looked at the state space representation. What does it mean for linear dynamical systems? Ordinary differential equations that are linear so that I can solve it analytically, and then depending on the character of the eigenvalues of the system, the response in what we call the state space can be different. It can be stable node or a saddle point or a closed circle. So there are many types of possibilities that are available depending on the eigenvalues. So the eigenvalues of the problem are very important in determining the stability. Now, how do we extend that to nonlinear systems is what we are going to talk about today. And in the next two lectures, when I was away, I guess 07 and 08, Mrinal introduced the ComSol for you guys, and he is going to put a recording of that lecture. Now, some of you who took this course on transport phenomena from me last term would remember this particular picture. What I'm going to do today and in the next few lectures is introduce the concepts of stability and dynamical response of systems, and then develop the algorithms and how do we go about piecing together the dynamic response of a nonlinear system. So the first thing we are going to talk about is what do we mean by stability. We already did that for linear systems. For nonlinear systems, the conceptual picture, I'm going to use two of them. One case is a situation where you have a round ball in a parabolic dish, for example. Okay. And if I give it a kink by applying a certain force, a small force, what would the response be like intuitively? It will basically oscillate back and forth, right? Will it continue to oscillate forever? No, damping. So what causes it to lose the energy and come to a rest is a dissipation mechanism, friction, for example. Friction with the solid or drag with the air. Both are dissipative mechanisms. If you didn't have them, if you did it in perfectly in a vacuum at a perfectly smooth surface, there is no friction, then it should go forever. Why? Because as it goes up, the kinetic energy is converted into potential energy, then it comes back, and the energy is not dissipated, it is conserved. Okay? Now that's a stable system. Now, if I have a finite boundary like this, and then I give it a large force, what would happen? It might actually go out of that, right? So we call such systems as linearly stable, stable to small perturbations. Okay, it doesn't say anything about large perturbations. It's very difficult to say anything about large perturbations. Another example is one where I just invert that parabolic dish. Okay, but I place that sphere on top, perfectly balanced. Okay, so that the weight acting down balances the normal force. Now, if I give it a small perturbation, it will not. It is an equilibrium position because forces are balanced. But if I perturb it with the slightest force here, it's going to go away from that, and that we would call as an unstable system. Now, if I have that in a perfectly horizontal plane and I give it a kick, what happens? It just goes to the new place and stays there, right? So that we will call as a neutrally stable system. And this is an extension of this where we have a non-linearly unstable system, meaning there is a well and small perturbations will bring it back, but a large perturbation will make it go to possibly another equilibrium point. That's another concept that you should understand. So I could have a situation where there are many equilibrium points, okay, and so it could go to any of the other stable equilibrium points, and all of them may be stable only linearly. Okay, that's the only thing that we can really answer. Nonlinear analysis is really still very difficult to understand. And how do we capture this mathematically, and how do we compute and determine the equilibrium positions and their stability is what the next few lectures are going to be in terms of the algorithms. This is another example. This was an example by a very famous fluid dynamicist by name Benjamin from Oxford University. It's a tricky example. I need to explain this to you, what is happening, and the response of this is fairly complicated. So we need to understand, and intuitively, we need to understand the response intuitively, and then we will look at a mathematical, possibly a mathematical representation of this. So what is happening here is you have a wooden block, okay, and into that wooden block you drill a hole, okay, and through that hole you put in some sort of a flexible material, a wire, okay, and you drill the hole at a distance a apart. So now we are introducing some quantitative measures to look at the response. So a is a control parameter. We can control it by positioning where the holes are, how far apart they are. And then I'm going to have the length, and this could be any measure, okay, the way that they have put the total length of the wire or the length to the tip, for example, from the base to the tip, which is going to be related to each other. Okay, so that's another parameter that I can control. How do I control that? By simply pulling and pushing on the wire on this side, because the wire is flexible, so I can push it and make the length larger, or pull it down and make the length smaller. Okay, and what am I going to observe? I'm going to observe whether the wire is going to remain in the plane when I look from this side, for example. Okay, that is, in here I'm looking perpendicular to the board. Okay, so from the side view or the normal view that you will see in B is the side view, okay, of A. B is the side view of A. And when you do that, for small lengths of the wire, you might find that the wire is stiff enough that it is staying vertically straight up. But as you increase the length, as you push the wire through, it will develop a slack. Okay, so it will start bending towards one direction or the other side. So it can bend towards this side, or it can bend towards the other side. So I can measure that angle, how far the deflection is. So that is my observed parameter. So you use this experiment to illustrate what we call as a bifurcation phenomena. That is a phenomena where for nonlinear systems you have solutions that are bifurcating, that are branching out, and there are multiple solutions, and their stability changes. And he made major contributions to understanding this in a classic paper in Journal of Fluid Mechanics, I think that came out in 1983 or something like that. Okay. So what we are going to do is we are going to do this experiment and plot the length against that angle for certain displacement, and there is another parameter that you can introduce that I will talk about later. Okay, so I'm going to do this experiment and plot the observed angle with the length. When the length is very short, what would you expect the observed angle to be? 0, right? So you do the experiment for very small length, you get a data point, you get another data point, and you get another data point. So as you continue to increase the length gradually, you will find that the displacement in the direction normal to it is 0. All of a sudden it starts bending towards one side or the other side. So there are two possible solutions. Okay? So you might find the curve doing this, goes up or goes down in a very symmetric way. So what we say is this is called a pitchfork bifurcation. The solution to the underlying equations. What would be the equations underlying this particular model? They will come from solid mechanics, rigid body mechanics, right? So the solid mechanics equations will allow you to calculate the bending, the deflection, etc. And when you solve that model, you will find this kind of a behavior. Now, the question that you can ask is, if I increase the length very gradually, very carefully, can I still keep it vertically aligned without it being bending one side or the other side? Another way of asking the question is that zero displacement solution still a valid solution to the governing equations? And the answer is yes. Okay. So, but what happens is those solutions that are represented by this dotted line are unstable. So the slightest wind, the slightest blowing on that will cause it to deflect to either one side or the other side. So this is a stable solution, that is a stable solution, that is a stable solution, but that is a solution but that is unstable. So if you calculate the eigenvalues of each one of these solutions, you will find that there is a positive eigenvalue corresponding to that dashed branch that you see here. Okay, I guess people won't be able to see it. I'm talking about this branch. If you calculate the eigenvalue of that branch, you will find that there is a positive value. Whereas for all the others, this one, and this one, you will find negative eigenvalues all through. Okay, and that shows that all those branches are stable. So it's a classic example of a problem having multiple solutions, stability changing at critical points like this. So in this case, as I said, it's called a pitchfork bifurcation point. So any questions on that? You have any questions here? You guys are clear? That? Okay. If there are no questions, I'm going to ask you to think about a variation on this. And the variation is going to be, instead of keeping this board perfectly horizontal like this, I'm going to start, in fact, in this view, the normal view, I'm going to start tilting it slightly. That's another control parameter I'm introducing. Now the tilt angle is beta. So this is not in the book by, this is taken by Dresen, from the book by Dresen on nonlinear systems. So it's a variation on that. So if I have that angle beta equal to 0, the response that I get is this one. Okay, so beta is a control parameter. Beta is 2 degrees now. I repeat the experiment. How do you think that figure will change? Do you understand what I mean? Beta is positive 2 degrees, the way I illustrated it. And my question is, how will this figure change for beta equal to 2? This is the figure for beta equal to 0. So imagine that the upper portion is the one that is for tilting in the right direction. Remember, this branch is for tilting in one direction, this is tilting in other direction. Both are equally possible when you have a vertically straight system and you're perturbing. Question?
No, I'm
Answering
answering.
it, okay.
You're gonna get a larger perturbation in the positive regime, a smaller one in the negative regime. It's not gonna perturb. So it'll be the plot will become asymmetrical.
The plot will become asymmetrical. That's a good observation. Okay. So if I replot it, let me try to do it here. Okay. So I will get a set of data points that are like this. Continuous curve. Okay. As I increase the length, it will preferentially tilt towards the right hand side because I have already given it a perturbation in that direction. What would happen to the other solution, the other branch? Can I ever get to the other branch? Does it exist? This part of the branch, does it exist for this kind of positive tilt? The answer is yes. Okay, all you need to do is, once you have reached that side, give it a large enough perturbation to go take it to the other side. This would physically mean grab that wire, push it to the other side, and leave it, and let it find its equilibrium position. So if you do that, and this is an important trick for your next assignment, okay, you should be able to do these kinds of tricks. So take that solution and flip it to the other side, and you'll get a point there. That is, you have made the wire find its equilibrium position on the other side for a tilted position with a certain length. And then you start decreasing the length. What do you think would happen? Okay, so you start pulling this down and decreasing the length. So you're going to get a point like this, a point like that, a point like that. And what would happen? All of a sudden, it will snap back to that. Okay? But, so if I want to connect these as continuous solutions, that's one. That's one solution that is obtained by gradual increasing of the length, and then through a large perturbation I establish this solution and I decrease it, and then it snaps back. Okay, so there is still an unstable solution, and that solution is this part. So it's stable over here, and then it's unstable. Okay? So that unstable solution gets connected like this. In branch tracing algorithms that Mrinal talked about in the last lecture, you will find if you are using such a continuation method, the solution will come like this and then turn back and go back. So we say that these two solutions have become disconnected. Okay, so a solution in that part is reachable, but the solution in the other part is not reachable unless you give it a large perturbation. What would happen if I tilt it the other way with minus beta, minus 2 degrees? This branch gets connected to the bottom one, and the top one gets disconnected. Okay, so this one is called a pitchfork bifurcation, whereas this one, this point will be called a fold bifurcation. Okay, so this one is a pitchfork. There are precise conditions that must be satisfied at each one of these points, and these are called singular points in the bifurcation theory for nonlinear systems. And we will see some of those singular points to be able to piece together the complex response of any nonlinear system. It occurs all the time in reaction engineering. It occurs in solid mechanics, buckling, failure modes. These are all causes of sudden change in the behavior of the system to varying forcing. And it occurs in fluid mechanics all the time. Okay. Any questions? Okay. What Brazen has in his book is a bifurcation diagram like this, and that is also possible. When is that possible? What I talked about, which Benjamin talked about originally in his explanation of this, was having a stiff steel rod that has less, more stiffness in some sense. Now, this is the same example, but what happens here is, as you increase the length, you get the solution going along this, and all of a sudden it jumps. Okay, and then its solution will continue like that. Okay, but if you start from this condition and start decreasing the length, it will not switch back here, but it will come back and flip back here. And that will be called a hysteresis behavior. Okay, and what happens if you focus on this zone? That will be called a subcritical pitchfork bifurcation. Because again, it is a pitchfork. Pitchfork basically means a fork should have a behavior like this, or like that. Okay, that's a fork. Okay, so this is like a fork like this, because there are, and the dashed line again represents unstable solutions. Solid line represents stable solutions. Okay, so this is one of the possible behavior depending on the stiffness of the material. So there are a lot of parameters in the problem: the tilt, the distance between the two holes, the stiffness of the material. They will all determine what the response is. The response can be very complicated. Now, the same thing, if you, for example, tilt it, you might find the connectivity change like this. Okay, whereas the top one remains stable but comes disconnected. Okay, and the lower part being unstable. So here now we have three limit points. This one will be called a fold or a limit point. This one will be a fold or a limit point. This one will be a fold or a limit point. And we will see later on what happens at the limit point. At a limit point, exactly one eigenvalue goes to 0. So we can use that condition to ask the question, where is that limit point? All I need to do is change the parameter, make the parameter as an unknown, but put the condition that the eigenvalue is 0, because we know at a limit point an eigenvalue is 0. So we need to reformulate our problem and then solve what we call an extended problem to answer and to track critical points like these. Okay? Any questions? The next assignment is going to be, I think, based on these concepts, where you will actually take a simple two ordinary differential equations, the steady state of which will have an algebraic equation, and you will solve them using continuation methods and stuff like that. Okay, this is an example of what we call a cusp bifurcation, which is a higher order bifurcation. And the previous example that I showed you does in fact have this kind of a behavior. Now we have for the first time an example of an equation. This is essentially that equation is equal to 0. Now if you had dx dt equal to that, it becomes a dynamical system, and the steady state of it is when this is equal to 0. That is what the equilibrium is. So we are trying to find out all those values of x for which this equation is satisfied in the parameter space A and B. Okay, A and B are the control parameters, like the length, like the tilt that we saw in the previous problem. Okay, so it's a cubic equation in this case, so you can actually analytically solve it in terms of A and B, and then map how that solution will look like. And so what we are plotting here is the state variable x against the two control variables in a three-dimensional plot, A and B. And this is the surface where f of x is equal to 0. As A and B are changed, and the surface looks like that. And that is called the cusp. essentially a cubic equation will have one point of inflection, okay, and that point turns out to be here. Now, if I take, for example, if I do the experiment, how do I interpret this graph? If I do the experiment that I did in the previous example, okay, where A is equal to the length and B is equal to the tilt, beta that I have, associated like this, okay. So when beta is equal to 0, plot for me from this diagram, how will that graph look like? Okay, beta is equal to 0, length versus x, but x is equal to the displacement, whatever we call it, theta or u. Okay, how would I construct that graph from this particular 3D projection? Look at it in the AX plane when beta is 0, B is 0. That is, cut this surface by the plane XA. Okay? And what you'll find is as you're going from there, there is a region where there is only one solution. Right there, you have the possibility to go on the upper surface. You have the possibility to go on the lower surface. There is also an intermediate surface. You have the possibility to go on the intermediate surface too. Okay? So you will get the pitchfork. Okay? Then take a plane that is beta equals plus 2 degrees. And what would happen? You will have one smooth solution that goes on the top and another solution that comes from the bottom, but this is going to be a bit tricky to draw for me. It will come on this surface, but then bend back and go on that surface. Okay, so it will be something like this. This part is on the middle surface. Okay, so very similar to what we saw in the earlier graph of unfolding of from this to this. In fact, it is exactly the pitchfork. The cusp is determined by what we call this unfolding. When this branch changes into this for positive beta, in the other way, continuously going down, then going up for the negative beta. So that is a classic example of a pitchfork bifurcation. So we are just talking about concepts, okay, of how complicated a nonlinear dynamical system response can be, even using a simple cubic equation like this. We already talked about the linear stability of stationary states. Stationary meaning things that are equilibrium. Okay, so you have a linear system. The stability is determined by the eigenvalue of that particular model. Now, if you have a higher dimensional model, you have a matrix. You need to find out all the eigenvalues of that matrix. Okay, that's one concept of a stability. That is, we say that the system is stable if the real part of lambda is negative. And that's a global result. If the system is linear, then the system is globally stable. What does that mean? No matter what your initial condition is, where it is, it will always go to that equilibrium condition because lambda is negative. So it will die. You will treat the y as a perturbation from that equilibrium system. So the perturbations will die down no matter how big the perturbations are. That's true only for linear systems. Now, the Russian mathematician Lyapunov generalized this idea of stability. This is a mathematical one I pulled out from the book by Dresen, just to see whether we can understand what they're trying to do, what he's trying to say in terms of the concept. Okay, so here, this is the kind of thing that you should be able to overcome after a graduate level course. Consider an autonomous nonlinear dynamical system. How many of you don't know what concept he's trying to talk about there? What is autonomous? What is nonlinear? What is dynamical? Pardon me?
I know the last two.
You know the last two, nonlinear and dynamical.
Autonomous, does that mean
No. No. Let's see. Anybody else?
Is that independent of the initial condition?
it cannot be independent of the initial condition. The initial condition is always needed. The solution has to. Say that again? Say that again? No, I think you are on the right track.
I mean, in other words, the final solution depends on the initial condition, but regardless of how you perturb it, it still gets to the same place. Steady state.
That is the concept of a steady state being stable, and that's what we are trying to generalize here. But autonomous means something. Mathematically, the mathematician will say a system is autonomous if you don't have time as an explicit parameter in that function. For example, if I have an equation like dx dt equals x squared plus 3x plus e to the power x, okay, that would be considered as an autonomous system because the function that appears on the right hand side does not explicitly depend on time. Okay, so, but if I have another example where I have dx dt equals e to the power x plus sine t, that would make it non-autonomous. Okay, and this is often the case when you're dealing with control systems. Why? Because you want to put a control action that is a function of time. Okay, so what is the advantage of an autonomous system versus a non-autonomous system? I think you hinted at that. It is not independence of the initial condition, but it is a trajectory that doesn't, you can shift that initial condition, the solution will remain the same. Like if I make the change, for example, in these equations, capital T is equal to T plus tau. Tau is a constant. This is the one variable, this is the transformed variable, tau is a constant. So all I'm trying to do is, instead of starting t equal to 0 now, I start the experiment t equal to 0 now, you start the experiment t equal to 10 seconds. Okay, so tau is 10, the time delay between the two of us is 10 seconds. That will make a big difference in here because time appears explicitly, so our trajectories will be completely different. Whereas if the equation is governed by the first one, your trajectory and my trajectory will be exactly the same, but I will be always 10 seconds behind you, following on the same trajectory. That's a conceptual way of trying to understand. Yeah.
And as a general rule, is one kind of equation harder to solve than the other? Or
No. Well, okay. That's a good question. The question was for the people in the PI, is a non-autonomous system more difficult to solve than an autonomous system? The answer is, when you're solving a system by analytical means, every problem is different and you need to develop a special set of techniques, particularly if they are non-linear. But numerically, the beauty is the algorithm will work irrespective. It's very easy to make a system that is non-autonomous to look like it is autonomous and then apply the same algorithm. And we will see some ideas on that when we look at ordinary differential equations, algorithms for that. The beauty of numerical methods is the same method will work no matter what the type of nonlinearity is. And that cannot be said for analytical methods. But analytical methods give you an insight that numerical methods cannot give you unless you do millions of experiments and absorb all the output somehow and make it part of your being to understand how the system will respond. A lot of the operators in the plant floor, they will know exactly how the plant operates. How did they get that experience? By simply tweaking it every day and observing. Okay, that is like doing millions of experiments. You have to do that for computer simulation. You don't get the insight that you'll get from asymptotic analysis, for example. Okay. Any questions for people at the PI? Or outside, I should say. Because there are also people from outside, not just at PI. Nope. Okay. If you have any questions, put them on the chat box and somehow raise your hand. There is a place where you can raise your hand on the top. And I will try to, if I don't observe, some of these people will observe and let me know. Okay, that's one part I need to figure out, how to make this interaction more effective. It's okay for people in person, but not for people outside. All right. So let's try to read this and see whether we can make sense out of it. Okay. Lyapunov, a Russian mathematician, proposed the following definition for what a stable system is, which is a very general system. Okay. So for an autonomous nonlinear dynamical system given by this particular equation, x dot equals f of x of t. Remember, t doesn't appear explicitly in f. F is a function of x, but x is a function of t. Okay, that still makes it autonomous. Where x of t is in an n-dimensional space, so there are n equations. Okay, B an open set containing the origin, and f is a mapping from D to Rn. Blah blah blah. The important point is the equilibrium of the above system is said to be Lyapunov stable. In fact, they named it after him. So we call a system Lyapunov stable if for every epsilon greater than 0, there exists a delta, which is a function of epsilon, which is also greater than 0, such that x0 minus xe is less than delta, means that xt minus xs delta is less than epsilon for every t greater than 0. Can anybody put that for me in English? It's like saying a legal document and translating it to English. You have a mathematical document, I want you to translate it into simple English. What does it mean? I don't know about you guys, but I am intuitive. Okay, there are two brains. I think I probably have told you, analytical and intuitive brains. So analytical brain can read that and understand it and say, okay, go to the next theorem or next definition. An intuitive brain needs to struggle with this to understand, maybe through a pictorial way, what do they mean by that. And we need to understand these concepts before we can go into the computers and try to implement some of this. This one is not as important for computer implementation, but important to understand what stability means. Anybody wants to try? Yeah?
So it's saying that for every epsilon, for every parameter that's greater than 0, there exists some delta, which is a function of epsilon, which is also greater than 0. Such that if your initial condition minus the equilibrium condition is less than that parameter delta, then there exists some value at some time t minus your equilibrium condition, which would be less than the epsilon which you want. So it's mapping, it's giving you a parameter by which you can judge the stability based on the initial condition.
Based on initial condition? Not necessarily.
No, it's x.
No.
Because of x.
Okay, let's try to put that some diagram on this. I think you have hit some key concepts there. Okay, is that clear for others? Do you want me to pursue this further, or you say, okay, I understand it, move on to the next? Let's try to put a figure in terms of the state space that we talked about. Okay, so this is a two-dimensional system. Let's say this is x1, x2. There are two state variables. Okay, and xe is the equilibrium point to that particular equation. That is, if I set f of x equal to 0 and solve for that, and I get some point. It is a point. That is, I will have a solution for x1 and x2 that satisfies that algebraic equation equal to 0. So I'm going to call that as xe. Okay, so we have kind of figured out what xe is. Now, what he is saying is, if I pick an initial condition such that the initial condition is close enough to xe, so there is a delta, I can draw a circle of a radius delta. Okay, so if my initial condition is anywhere inside that circle, this condition is satisfied. Okay, that means I can find a delta and I can put a circle and what happened? Any questions? No? Maybe it's just my hand. When I get excited too much. So I can find a region delta, I can draw that circle, and if my initial condition is anywhere inside that, that's what this part says. x naught minus xe less than delta simply says my initial condition is inside that. So if I start in that region, the next part it says is then xg minus xe less than epsilon. So I need to find another value epsilon and draw a circle. That circle may be bigger than this, okay, with a radius of epsilon. And it says the trajectory x of t minus xe, that is how far that particular point is from the equilibrium point. That trajectory will always be less than epsilon. I can find an epsilon so that it will always be remain inside that. So it depends on me finding these two numbers, epsilon and delta. Okay, and what it says is if I start from within delta, I will remain within epsilon. That is his notion of stable. Why is it so nice, so powerful, so general? Why is it so nice and powerful and general? I think it's a very nice and powerful and general definition of what a stability is. It's just a definition. It's a concept. What he's going to do with later on, I will show you. But at this stage, he's just introducing, this is my notion of what a system is stable. We already talked about a system that is stable, whose eigenvalue real part is less than 0. So it is asymptotically stable. As time goes to infinity, it will go towards xe. This one doesn't say that. This one simply says if I start within delta, I will remain within epsilon. And as long as it doesn't go out of epsilon for all time, it is a stable system as far as I'm concerned. Right? The beauty is it includes all limit cycles, all planetary motions that are just going in cycles. It doesn't go towards the equilibrium position. There is no point in the fixed state space that it goes to, but it remains confined. So it will include concepts like chaotic dynamics, which we will see later on. Okay? Are you familiar with what a chaos is? Have you heard of it, at least conceptually? That's a system where the response seems to be completely random, but remains bounded in a certain domain. And the concept of chaos was introduced in the 60s. This definition came out 100 years before that. Right? So it shows the power of his ability to think generally, even before the concept of what a chaos could be. He was able to conceive of a definition that will contain and point to those systems as still stable systems. They are not unstable systems, they are stable bounded systems. The next part is the equilibrium of the above system is said to be asymptotically stable. Now he is adding other attributes. If it is Lyapunov stable and there exists a delta greater than 0 such that if this is true, then limit t going to infinity, the trajectory goes to 0. This is what we started off with. As time goes to infinity, the trajectory from the difference between the trajectory and the equilibrium point should go to 0. Then we will call that as an asymptotically stable system. It remains bounded, it is still a stable system. And it is called by different names in different books, an equilibrium system or a Lyapunov stable system. And that is the only reason why I wanted to bring this out, because it's a very general notion of what stability is. And the equilibrium of the above system is said to be, this is not a very powerful generalization, said to be exponentially stable if it is asymptotically stable and there exists alpha, beta, gamma such that if your initial condition is confined in delta, your trajectory is confined forever in this particular form. That is, it not only goes to 0, but it goes to 0 exponentially, because you can find a beta, you can fit that response to that behavior. Now, all linear systems, when you take a nonlinear system and linearize it around a steady state, you will find them to be kind of exponentially stable if they are stable. Okay, because the solutions are typically in terms of eigenvalues expressed as e to the power something. So the reason I point this out is that it's a very general definition, and it will allow us to include a lot of concepts of stability. Question?
The third one, exponentially stable, but how much more practical is that than asymptotic? It seems like it's
No, remember, he's a mathematician, so he needs to define all these very precisely. So from a practical engineering point of view, you can ask, is there any other type of stability? Why are we bothering about defining this? Okay, and the answer is yes. When does that happen? Think about it. If I have a solution to a problem that has a repeated eigenvalue, how do I construct the solution? If I have two distinct eigenvalues, then it will be x to the power lambda 1t plus x to the power lambda 2t with a constant. But if they are repeating it, then it will be x to the power lambda 1t plus t times x to the power lambda 2t. There are some algebraic expressions that come into the solution. So these will be called algebraic kind of growth or decay in the solution. And in fluid mechanics, it is thought that early stages of onset of turbulence, even in laminar pipe flow, is caused by that kind of degeneracy where some of the eigenvalues are repeated. And so it's not always purely exponential decay. Okay? And that's probably why he thought about it already then and put that in, or it may have been added later on. This is taken from a textbook. I have not seen the original paper. Okay, any other questions? Okay. Yeah, I think this is what we just explained. Now, Lyapunov also developed a method which is called the second method. There is obviously a first method, which is the direct method in some sense. Second method for stability. How do we determine stability? This is a beautiful idea. How do we determine whether a system is going to be stable or not without solving for eigenvalues? Because solving for eigenvalues is a very challenging task, particularly if you have very large systems, or partial differential equations and stuff like that. And this is taken from Wikipedia. Essentially what he says is that a system is stable if we can find one function v of x. So it depends on our ability to find this function. It's called the Lyapunov function. It's a scalar function of the state vector x. X is a vector. If you have n equations, you have n x components in x. But v is a scalar measure, that is, we define from x. And he doesn't prescribe a formula for how to define that. So in the 60s, there were a lot of papers on how to develop this Lyapunov function. It's called a Lyapunov function. How do we develop that for CSTR, for various kinds of chemical engineering problems? But basically what he says is, if that function v of x with the equality if and only if x is equal to 0, that means essentially a function that is positive definite, meaning v of x is equal to 0 only if x equal to 0. Otherwise, v of x is always greater than 0. Okay, what does that mean? It's a kind of a quadratic function, okay, with a parabolic in the simplest case you can think of. And if the v dot, that is d dt of vx, is less than 0, again with equality only if and only if x equal to 0. So v must be positive definite, v dot must be negative definite. Then v of x is called a Lyapunov function candidate, and the system is asymptotically stable in the sense of Lyapunov. So that's all you need to do for a given system. If you can find a function which has this property, then you can conclude that system around that equilibrium point is asymptotically stable. What does this mean? People have since then tried to give a physical meaning for a mathematical function, and often the physical meaning that is given is this v is some sense of measure of energy. Okay, so all you are doing is constructing a function that's a measure of the energy of the system, and it is seeking the minimum of that energy surface. Okay, and if that is true, then the system is stable, asymptotically stable. And there are some examples of that. So for a given system, if you give me a system dy dt equals f of y, okay, I need to first find that function v and then find its v dot, the derivative. So what is the derivative? The derivative dv dt is, if you use the chain rule, Remember, the way that we propose this, v is a function of x, or in this case y. I switched the symbol once again, sorry. Y is the state variable. Okay, so v is a function of y, and I'm trying to calculate dv dt. Okay, y is a function of t. So the v dt will be by chain rule dv dy dt. Okay, but dv dy is a what is it? Is it a scalar, a vector, or a v is a scalar function, but it's a scalar function of a vector. This is a vector. The state is a vector. Okay, this is a scalar. Okay, so so v is a scalar, but I'm taking it with respect to y, a vector. So that is going to be the gradient operator. That's what this gradient of v is. Okay, so that is a vector, and so you're dotting it with the dy dt, but dy dt is the same as f from the original equation. Okay, so this is how you test whether a particular system is stable, by knowing what that f is. From that f, you construct this quantity, gradient of v multiplied by f, and check whether that is negative definite. So the idea would be dream up with some function v, okay, and then use that v to calculate v dot, and make sure that v is positive definite. Okay, and once that is positive definite, apply this test. And if it is negative definite, that means you have a system that is asymptotically stable, guaranteed to be. The beauty of it is you don't need to know the solution itself. You don't need to construct y. You don't need to construct y as a function of t. All you need is come up with this function v. Okay, then you can apply this test quickly, using only f, not the y. That is the power of general analytical methods. There are very few methods like that for nonlinear analysis, and this is one of the methods. It's still not very useful because the onus of finding what v is on to us. How do I find that v? Okay. Any questions? Here is an example of a 2 by 2 system. Y prime is z and z prime is minus y minus 2z. Put it in the matrix, vector matrix form. Okay, and let us consider, that is, someone has dreamt up this particular function. But you can see that it is a quadratic function. It has to be positive definite, right? So if you write it like that, it will always be positive definite. So that's obvious. Okay, so this is going to be greater than 0. And then I can calculate dv dt according to the recipe that I just gave. And you will find, because this is always positive, I have a negative sign, it is negative definite. So this system is stable without solving the eigenvalues for that particular 2 by 2 matrix. But you can verify that, and I think that is done somewhere. I guess I didn't. Yeah, here it is. The eigenvalues are minus 1, minus 1. Okay, did you have a question?
For any given system, A, is there always such a function B? And B, is it unique?
The answer is no and no. If that is known, then universally all systems are stable. Right? You will find systems that are not stable, that are blowing up. Right? So the obvious answer is that it is not true. And a lot of papers, I think my own supervisor was a numerical methods person. He has several books, Leon Lapidus. And question?
She asked what my question was.
Yeah, okay. Thank you, Rashid. I think now we can test how this system works. I didn't notice it, but the students here did. What was the question?
My
What?
question. He asked what my question
Oh, what was his question? The question was, for every problem, correct me if I got it wrong, every problem, is there always a function v that will satisfy this condition? And if it is unique.
Is
Is it unique? Okay, the answer I said is no to both. It's certainly not unique, and it is certainly not obvious that you can find it for every system that one can write an equation for in nature or want to study in nature. Obviously, there are systems in nature that are unstable, that blow up. Every explosion, every chemical reaction that explodes is an unstable system, right? So that was the discussion about. Okay, is that clear to you guys? Any other question? Okay, keep doing more of this. I like it. All right. Region of attraction. So this is another concept which is actually building on your question that you raised. The question was, can I find such a V for every system? The answer is no. And then people started asking questions, can I at least construct some function, because I don't know how to begin constructing that function. That's the challenge, right? So can I at least construct that function and then ask the question, over what region in the state space that condition is satisfied? That is, V remains positive definite and V dot remains negative definite in a certain region, may not be globally. Then I would define that region as a region of attraction. So if I lie within that state space, I will be stable. If I go outside of it, I cannot answer the question. Just because I have not been able to construct a V, it doesn't mean that it is not stable. Okay, so I can identify a region in the state space, something like this. Inside that region, V is positive definite and V dot is negative definite. And if I can do that, I can then say that that is the region of attraction for that particular system. So if I start anywhere in the state, it satisfies the conditions of stability and it will be attracted. But it does not answer the question. If I have a point outside, does that mean it is unstable? The answer is no. It may also remain stable. That is because there is no uniqueness to V. The map that we construct for a region of attraction is not going to be unique also. Then the challenge becomes, how can I construct V such that I can map out the largest region possible? Okay? But pretty soon you find that kind of analysis, initially when you pose a question, is interesting, it leads to papers, but then you do the same thing and apply to 10 different systems, the novelty wears out. And then people stop doing those kinds of things. But in the 60s and 70s, you will find a lot of papers that talk about constructing Lyapunov function and exploring the region of attraction, etc. So here is an example of, again, these are all taken from the book by Drazen is an excellent book, Nonlinear Analysis, a simple book. So here he has a nonlinear equation. Okay, you can see that it is a cubic equation with some initial condition. The initial condition itself is parameterized. Y0 is some value z. But is it, I could change z. I could change the initial condition. And I'm trying to get a solution in terms of that. And the analytical solution for that particular problem is this. Okay, and alpha is greater than 0. So what should be the nature of this solution as t goes to infinity? Is it a stable system? It's a nonlinear system, so what is the solution? How many solutions are there? It's a cubic equation, so there are possibly 3 solutions. Clearly ys equal to 0 is one solution, right? So as t goes to infinity, does this go to 0? The answer is yes. Why? Because this one is in the denominator, luckily. As t goes to infinity, that's going to blow up. That's going to become a large number, but you're going to take a square root of that and divide by that, so 1 over large number goes to a small number. So that is a stable system. Okay, but is that, what would be the trajectory for the following case? For example, if I have this is a one-dimensional case, so it's going to be a bit difficult to imagine it. Imagine this as your state space, one-dimensional state space, a line. Okay, and here is your solution, ys equal to 0, the origin. Okay, and here is alpha. So if I take a z that has the same value as alpha, what happens to that term? It becomes 0, right? Then what happens to the steady state? It's just alpha, but it is not the steady state corresponding to y is equal to 0. So if I start with that, I'm not going to go to that steady state. Okay. So when you have multiple states, each state will have a region of attraction surrounding it. And if you are within that region of attraction, it will go to that steady state. Okay. So if, for example, Z is very large, what happens to this? 1 over Z becomes very small, and you have a negative number, right? And you're going to take a square root of a negative number. Okay. So again, it's not going to give you a solution that is going to go to y equal to 0. That solution is not accessible for large values of Z. So there is a region of attraction for each steady state solution. That's the point I think that we want to drive with this particular example. So the concept of what a region of attraction is, multiple steady states, etc., you should be familiar with. And the next important thing is we are now beginning to construct algorithms. Okay? And for nonlinear systems, the way that we study nonlinear systems is locally linearizing them and assembling the effect of that to get the full nonlinear picture. So linearization is a very important concept. You would have seen this many, many times before in process control and even in the transport phenomena course. But let me just go over it very quickly. And if you have not seen it, slow me down. Okay, so here I'm going to start with a two-dimensional system. There are two state variables, y1 and y2, two functions f1 and f2, and these are the initial conditions. If I ask the question, how many solutions are possible in this two-dimensional space? Okay, y1, y2, sorry, y1, y2. I cannot answer that question beforehand. There is no theory today in mathematics that will tell you how many equilibrium points are there for that particular set of equations. Okay, but if I know one of the solutions, then if there is a parameter in the problem, for example p, okay, I can continue and trace out all the other possible solutions. But I must know what that one solution is. Benjamin contributed a lot of the ideas on the number of solutions, how the solution number changes with the parameter change, which is the topic of bifurcation theory. So there is something called an index theory that he contributed a lot to in trying to help us understand complicated dynamical systems. But what we are going to do is we are going to learn how to linearize the system. And that simply means I'm going to approximate this equation by dy prime dt equals a y prime. Okay, that is a linearization process. And now that linear model is valid only around a steady state. So you give me different steady states, I can develop that model. So the matrix A will depend on the steady state itself. Okay. How do we do that? We do that by proposing the following. We're going to say that y1 of t is going to be equal to y1s plus y1 prime of t. Okay. So the state y1 depends on the steady state value plus a departure from the steady state. So you can think of this as the perturbation, which is a function of time. But the steady state itself is not a function of time. So you have a similar equation like that for y2. And if you have an n-dimensional system, it just carries forward in the same way. y2. And this is what I call y2 prime, y1 prime, the perturbation of it. So you take this definition, put it back into your nonlinear equation in here, okay, and do a Taylor series expansion. Okay, and when you do that, you will end up with this linearized equation. Okay, so if I substitute on the left-hand side, I'm going to get dy1 prime dt. This is the first equation. Because y1s is a steady state, when I take its derivative, it's going to be 0. Okay, so that term drops out, and all I have is y1 prime dt. And on the right hand side, I have f1, but f1 is a function of y1 and y2. So I need to write this as y1s plus y1 prime, comma y2s plus y2 prime. I need to do the same thing for the second equation, but let's just look at the first equation and look at the right hand side. So it is still a nonlinear function on the right hand side. f1 is a nonlinear function. It's a function of y1 prime and y2 prime, which are functions of time. So if I do a Taylor series expansion on this, how would I write that? Now the Taylor series expansion is around a steady state. The steady state is y1s, y2s. So in a state space, there is a point. Y1 and this is Y2. I have some steady state. Okay, I label it as S with a subscript S. So Y1S, Y2S represents these two distances. Okay, so I'm linearizing it around that steady state. So when I do the Taylor series, what will I get? I'll get F1, Y1S, comma Y2S plus, what would be the Taylor series? df1 dy1 evaluated at the steady state multiplied by y1 prime. If I'm not making sense, please do stop me. Okay, I'm assuming that Taylor series is something that you can recall. Then the second variable, it's a multivariate Taylor series, two variables in here. So it's going to be df1 dy2 at s times y2 prime. Plus, there will be higher order terms that we are going to neglect. Okay, but what is the first term by definition? Is 0. Why is it 0? Because y1s and y2s make that function equal to 0. Okay, that is the steady state. Okay, so this function is equal to 0. Okay, so what I'm left with is dy1 prime dt equals dy1 df1 dy1. Let me call it as a11. A11 is this term. Okay, y1 prime plus a12 y2 prime, and a12 is this term. Now I can calculate these numbers because I know the function, so I take the derivative of the function with respect to y1 and evaluate it at the steady state. That's how the steady state gets into the problem. Okay, so a1 and a2 depend on y1s and y2s, the steady state values. And when I do the same thing for the second equation, I will get y2 prime dt. This is the first equation. This is the second equation. Okay, and this will be equal to a21 y1 prime plus a22 y2 prime. And this is what I write in vector matrix form as dy prime dt equals a y prime. A is that matrix consisting of these four coefficients, a11, a12, a21, a22, evaluated at the steady state. So this is the Jacobian matrix evaluated at the steady state. And the eigenvalues of this Jacobian matrix determine the stability. If it were a completely linear system, we already know how to solve the solution. Now what we are saying is it is a nonlinear system, but we are locally linearizing it. We have neglected the higher order terms. So whatever we can say about the stability is valid only in that region. Okay, for small perturbations, y prime is supposed to be small. That's the process of linearization. And this is so important for solving by Newton method, for solving by Euler-Newton continuation. Did we not talk about it last lecture? Continuation methods? Not clear? Okay. I will again go over it. Any questions for people in PI? Okay. Okay, before we do this, let me just, that's why I guess I left a lot of space. Let me just look at, so we have a linear system and we have related now how to get the stability of a nonlinear system for local perturbations. Okay? Linearize the process, get the eigenvalues, and everything that we have seen for linear dynamical systems, either being a node or a saddle point, all those concepts will carry through for this particular problem. So how do I find the equilibrium solution? Before I can calculate these coefficients A11, A12, A21, A22, I need to know where the steady state is in the state space. Okay? How do I do that? So if you give me an equation dy dt equals f of y with some parameter t. Okay, that is a dynamical system. I know how to linearize it and I know how to calculate the stability, provided I know how to find the steady state solution. That means for steady state solution, I need to set this equal to 0 and solve only this part. What kind of numerical algorithms are there? Now for linear system, we know how to solve. Gaussian elimination, conjugate gradient method, GMRES, etc. There are a number of methods that we solve. But for nonlinear system, what do we do? The methods that we have seen can be extended. The method of successive over-relaxation, they can also all be extended to the system. But the only method that I'm going to talk about is the Newton method. Okay. So here I'm going to treat P as a parameter that is known. So the only unknown is y, and I need to satisfy these n equations in those n unknowns. Y is a vector of length n. Okay. So do you recall what the Newton method is for a one-dimensional system? 1D case, which is f of y equal to 0. Just one equation in one unknown. Geometrically or graphically, what it means is we are going to plot that function f of y, and that function is like this. And you need to find that value where the function is equal to 0. So in any iterative methods, what do? We make a guess and we develop a method to get better guesses and apply that repeatedly. So in the Newton method, we make a guess, for example, x0, and at that point you draw the tangent and ask the question, where does that tangent intersect? So that is linearization again. Okay? A nonlinear curve, what we are saying, if the curve were linearized at that guess, what would that line look like? And where does that line intersect? And that's going to be my next guess. Then I say, okay, if that is a guess, what is the tangent there? And where does that tangent intersect? And that is my next guess. Right? And when you capture this geometrical idea for the one-dimensional case, it simply becomes xj is equal to, or j plus 1 is equal to xj minus f divided by f prime at xj. That is the Newton method for one-dimensional case. And it is simply, conceptually, it is simply the following. Make a guess, draw a tangent. That is why you need f prime. F prime is the tangent. Okay, and you need f also. So using these, you fit a straight line and ask where does that straight line intersect the x-axis. Okay, when you apply that logic, you get this one-dimensional version of the Newton method. So the multi-dimensional version of the Newton method is a generalization of this. So multivariate case is xj plus 1 as a vector is equal to xj, the previous guess as a vector for n equations, minus, we call this as I guess A inverse F. But what is A? A is the Jacobian matrix that we talked about earlier. Okay, and if you want to write it in an expanded form, it will be a matrix consisting of df1 with respect to dx1, df1 with respect to dxn, all the way to dfn with respect to dx1, dfn. So the same matrix, the Jacobian matrix, which you can construct once you are given what that function is. If you know the function, it's essentially derivatives of these functions with each one of those variables. Okay, you can construct that matrix A, and you invert that and multiply it by F, and that gives you what we call a correction. So you can think of this as equal to xj minus delta j. So delta j is that correction. What you have done is you have converted the problem of solving a nonlinear algebraic equation to repeatedly solving a linear algebraic equation. Okay, so all you have to do is solve this equation A delta is equal to F. Delta is your correction, A is your Jacobian matrix, and F is the forcing function. So as F is driven to 0, delta will be driven to 0 also if A is non-singular. Okay?
If A is what?
Non-singular, meaning its determinant is not 0. Okay? Why is that important? At critical points it is important because when you have a limit point, it turns out that one of the eigenvalues is 0. If the eigenvalue is 0, the determinant is 0. So the J is not invertible. Okay? So when you're dealing with nonlinear tracing of solutions, there could be certain values of the parameter where A becomes non-invertible. Okay, then you get into problem, and we need to overcome those problems. So essentially what we have done is we have reduced the problem of solving a nonlinear equation to solving a system of linear equations with repeated values of F forcing on the right hand side. Where are those F's calculated? And the current guess values, right? You make a guess and you put the guess into the function and check whether the function is 0. If the function is 0, you have made the right guess. If not, you plug it onto the right hand side and you have already A, and you can calculate the delta and subtract the delta from the previous guess and gives you the next guess and repeat that process. In COMSOL, I guess you have something called delayed Newton. Did you talk about it? Delayed Newton method. I thought I saw it in the notes that he sent me. You didn't talk about it? What do you, if somebody says, I'm using a delayed Newton method, what would it mean? What would you guess that it might mean? You are delaying the Newton method. That's what it means. A delayed Newton method would mean that you are delaying the convergence of the Newton method. Okay? What that would mean is you're going to calculate the delta from this equation, but you're not going to apply the entire correction. You're going to apply only a small fraction of the correction. So you're going to put a multiplication factor here, alpha, which is going to be less than 1, for example. Damping factor. You heard? Okay, I'm using the wrong terminology. Damped Newton method. Damped Newton method, right? So the idea is, why would you want to damp the Newton method? In fact, you should not damp the Newton method, otherwise it won't converge as fast as it would normally converge. Okay? Newton method converges quadratically. What does that mean? It's again a proof, the theorem of proof. It is again a theorem and a proof, but what is the meaning really of what quadratic convergence means?
On the order of x.
So maybe we will do this error analysis in the next class. If the error is 10 to the minus 3 in one iteration, you do one more iteration, it's going to go to 10 to the minus 6, 10 to the minus 12 next iteration. That's what we mean by quadratic convergence. But if you dampen it, you're going to lose that. The reason for dampening it is Newton method also has the requirement that quadratic convergence is valid only when you're close enough to the solution. But you may not know initially. To begin with, the initial guess may not be close enough. So you apply this. These are all practical tricks that COMSOL and Fluent will use to enhance the range of, so that you can throw any initial guess and it will still hopefully converge. Okay. So the Newton method and the Jacobian is going to play an important role in the next couple of lectures, where we develop the continuation method, the arc length continuation, the Euler-Newton continuation, and tracking of the singular points. And that will give us a very strong foundation for analyzing any nonlinear algebraic system. And then in the course we are going to reduce nonlinear differential equation to algebraic equations. Okay? So from linear to nonlinear, we're building slowly. And then we will see discretization methods for partial differential equation, ordinary differential equation. In every case, we'll convert them ultimately to a nonlinear, and finally use. How do you solve this one? You need to invert, right? That's LU decomposition. Right? So that's the building block from which we are building everything else. Okay, I think we'll stop there today. Any questions, guys? Those who are on the net? Damped Newton. Thank you, Mrinal. Okay, so see you on Wednesday.